All right, so today we're going to continue on with spectroscopy. I'm pretty sure that after this, we're going to take a break from spectroscopy for a little while. I really don't like, I mean, for the sake of the students, I don't like to cover all of it all at once. It's a completely new idea and kind of a lot to digest. So we'll do some traditional organic chemistry and learn about aromatic compounds. That's chapters 15 and 16. All we know really currently officially is that we've made it very clear that benzene is not an alkene and it does not behave like alkenes do. So we're finally going to learn how it does behave and compounds like it. But today our topic is mass spectrometry. And you'll notice I said mass spectrometry instead of mass spectroscopy. People, again, sometimes do call it mass spectroscopy. That's technically not correct because mass spectrometry is technically not a spectroscopic method. In other words, it doesn't work by the molecule absorbing a photon of electromagnetic radiation, undergoing a transition, and giving us a peak on the spectrum that way. Rather, mass spectrometry involves literally blasting the molecule apart. And there's a few different ways that we can do that, but mass spectrometry has been compared very much to you have this wonderful Rolex watch and you hit it with a sledgehammer and it flies apart into a gazillion pieces. And you learn something about the watch by studying those gazillion pieces. Uh-oh. Well, we're getting into something. Oh, yeah, she has to be on top of my printer for some reason. Anyway, sorry about that. I have to learn not to get so distracted by the cats. Don't think there's too much in here that they can break. Anyway, we're going to, as I hope you picked up in the reading, we're going to cause our molecule to fragment to form pieces of the original molecule. And from that, we can learn something about the structure of the molecule. I don't consider it to be terribly possible to look at a mass spectrum and know what the compound is. At least that's not a focus of mine. That's not the sort of thing I tend to ask. However, you're going to have some OWL questions like that. And in order for that to be an answerable question, you know, here's the mass spectrum or here's the mass spec data, what's the molecule? There's only a very few particular molecules that will work for, and they have to be small. You know, they have to have really small molecular weights. They have to be things like ethylene or ethane or chloromethane. Then maybe, because you can almost just get it from the molecular weight. So I've summarized, actually, I can sort of do this like they do on, on YouTube and even on Twitch. I've summarized over there the main ideas behind mass spectrometry. My goal for us is basically to understand what it is and how it works, and then maybe to get some idea of what we can deduce from a mass spectrum of a typical organic compound. But as to here's a mass spectrum, what's the compound, not really possible. Again, like I said, unless the molecule is really small and has a very small molecular weight. You know, if your molecular weight shows up as 30, there's very few things that have a molecular weight of 30. It pretty much has to be ethane. And you'll see that when you get to the OWL assignments for mass spectrometry, which, by the way, should be up and running. We had a bit of an issue. For some reason, you guys could see it, but my section 515 couldn't. That is not supposed to happen. So that's yet another thing on my list that I have to figure out what's going on. But as I said, nothing's due for grading until Friday. One other thing I should mention now that I'm on the topic of OWL, just a reminder, if it says the assignment is not graded, you can always trust that. I'm never going to change not graded to graded. The assignments that usually are graded are, of course, going to be the mastery and EOC assignments, except you'll notice, especially this semester, on occasion, the mastery assignments also will not be graded. And the reason for that is sometimes they only give me like 3 or 4 questions. And I don't like making those graded. I feel that's a little too much pressure on the students. You know, 2 or 3 points out of 10 per question. I don't like that. I'd rather just make it not graded. But in any case, you never need worry about that. If it says not graded, it's not graded. I'm not going to change it on you. Good. So we've already said this over here. Mass spectrometry works. Let me see if I can't make that a little bigger. But mass spectrometry, well, actually, I already made it bigger. I made the font larger. I may need to enlarge down at the bottom. But basically, the thing works by knocking out an electron from a neutral molecule, and that leaves us with a radical. And that electron can and will be from anywhere. It can be an electron in a bond, which I'll demonstrate down below. It can also be a non-bonding electron. Actually, non-bonding electrons, like in lone pairs, those are higher in energy than bonding electrons, aren't they? So they're easier to knock out. Either way, you get this. You get what's known as a radical cation. You get something that has an unpaired electron somewhere and also has a plus charge by virtue of having lost an electron. And this thing, by the way, is generally abbreviated M plus dot. And I can't really write it here the way it's usually shown, though you'll see it both ways. You'll also see kind of the dot plus the dot and the plus sign kind of above and below each other. Let me make that a little bigger so you can see it. What about 18 point? So something like that. That's usually, you'll sometimes see it printed like that. That's how I will tend to print it, like if I have to put it on the exam, let's say. But that M is a shorthand for the molecular ion. Yes. And the reason they call it that is it's exactly what it sounds like. It's the whole molecule that's made into a cation, an ion, by virtue of having knocked out one electron. So that's why they call it that. In other words, this molecular ion is going to have the same molecular weight as the whole molecule, because all you've knocked out is an electron, and those weigh basically nothing, right? An electron is, somewhere around in about 1/1800th as heavy as a proton or a neutron. So electrons essentially don't weigh anything. So from the molecular ion, hopefully you got at least an idea of this from the reading. From the molecular ion, we get the molecular weight of the compound. And that's one bit of information that we get from all this. Now, there's all sorts of different ways things can fragment. We'll just go over some of the more common ones here. I often get asked if you have to know about all of the other kinds too. It's always better to know more than to know less. Again, we're going to be doing our exams open book and open notes. And you already know, of course, that spending a tremendous amount of time looking stuff up and is going to be counterproductive because you'll run out of time. And certainly if I do my job right, it's not going to be that you'll be able to copy out of your notes or the book great swaths of answers to questions. But some of those things, though, I'm going to have to leave you to read about on your own. We're really only going to have time here to talk about the most common types of fragmentation. But I like dwelling on this stuff here at the beginning because to me, in my experience, these things that we're talking about now are the most confusing things about mass spectrometry. Once you look at a bunch of spectra, just as I said with infrared spectra, maybe we'll look up a few of them today. Once you look at a bunch of spectra, I think you'll get the idea of what kind of things to look for, what kind of things you can deduce from mass spectra. Oh, and by the way, I don't have a reef polling thing for today, so we're just taking attendance. So please do register your attendance. That will just be a free 100 out of 100 for today. So where were we? Oh, so we form this molecular ion, and that radical then fragments into another radical plus one carbocation. And here's the first big sticking point. What students will very reasonably ask at this point is, well, where is that radical and where is that cation going to be? And the answer is they can be anywhere and eventually will be anywhere. All possible covalent bonds will be broken, and all possible places where you can form a cation will eventually be found. So you'll see all possible fragments. The only thing is not all cationic fragments are created equal. Some are more stable than others. And so that's why you'll see different amounts in the spectrum of each of the different possible ions. The idea being the ones that are more common are the ones that are more stable, and so you'll get taller peaks. But that's really all that mass spectrometry is about. It's about adding up molecular weights of all of the different possible fragments. And you know how to do that from the periodic table. You'll just look up the different masses of at least the most common isotopes of the different elements. So for carbon, you'll of course use 12. For hydrogen, you'll use 1. For oxygen, you'll use 16. Can the other isotopes play a role? Sometimes, very occasionally. Usually not a big role, except for those elements. The ones where you really have to look out for it are those elements where you have two isotopes that are very similar, or at least somewhat similar in relative abundance, like chlorine 35 and 37. About 3/4 of all chlorine is chlorine 35, and the remaining quarter is chlorine 37. So you'll actually see both in the spectrum, the peak that comes from the chlorine 35, and then 2 AMUs higher, the peak that comes from chlorine 37. Another one that you'll notice is bromine. There you've got bromine 79 and bromine 81, and they're almost equal in abundance. I think it's something like 55-45 or 53-47 or something like that. They're pretty close. So you'll see these two peaks that are 2 AMUs apart that are almost equal in height. That's a dead giveaway that you've got a bromine in the molecule. So that's why you'll notice that, I think, you'll get some questions like that in OWL where you actually can tell what the molecule is just from the mass spectrum, but they've got to be very small molecules. You almost never can do that. What I'm going to focus on is being able to look at the mass spectrum of a compound and pick out some of the fragments. Just like I don't expect you to identify every single peak in an IR spectrum, I certainly don't expect you to be able to pick out every single possible one and identify every single peak in a mass spectrum. That's generally not possible. So how many should you be able to identify? Well, I don't know. How about we start with 1? See if you can get 1. That's always good. And if you can get 1, you can probably get 2. Generally 3, 4, 5 come pretty easily. 20 is probably too many, but if you can do a few, you're probably in good shape. Again, I'll remind you, I've put an old exam on eCampus. You'll get an idea of possible question formats there, also from OWL. I don't promise I'll use the exact same question format. Mass spectra also can be dealt with fairly well using matching. Here's 4 spectra and 6 structures or 5 structures or whatever. Identify what the compounds are, and you can usually do pretty well with something like that. But in terms of, here's the mass spectrum of a fairly large molecule, what is the molecule? That's generally not possible. Good, so where was I? So we already said the radical can be anywhere in the molecule. I think I covered this in the notes. And so the bond that breaks can and will be anywhere, and eventually you will get all possible bond breakages. Every single bond that can break will break. Now, you won't be able to see all of the fragments necessarily, but all of the ones that are of reasonable stability and therefore reasonable abundance, you'll see. And another thing that I really want to stress that I think is confusing at first, please be aware that in order to be able to detect the fragment, it must be charged. And the reason for this is in how mass spectrometers are made and put together. I should also mention this, by the way. You'll certainly find in your book a beautiful diagram of a typical mass spectrometer, showing you what all the different parts are and what they're called and what they do. This is not an analytical chemistry course on experimental methods. I certainly would never expect you to be able to draw a gorgeous diagram of a mass spectrometer. And again, if you go on to analytical chemistry, you might be, but I don't think that's the focus of this course. But it is still important to be aware that in order to be detected, a fragment must be charged. And really, for our purposes, it's always going to be +1. Now, can you get fragments with multiple charges? Yes, that is possible. But that's, those are generally pretty unstable. So to get anything that you could detect would be pretty rare. And certainly, if I'm looking at a mass spectrum, I'm going for the easy peaks first. I'm not going to bother with things that are +2 and +3. I think there's going to be half a dozen other peaks that are +1 that I will be able to identify. Good, so here I'm showing how it is that you can knock an electron out of a bonding electron pair. You then wind up with some bond somewhere in the molecule between atoms that I'm just calling A and B generically, and you'll get from that fragmentation a cation, which you'll detect, and a radical, which you will not. Of course, I could just as easily have drawn this half arrow the other way, and then I will get the A radical and the B cation. So you see, you'll get both. That's how it is that you'll get all possible fragments. Remember, and this is actually one of the harder things in organic chemistry, is to remember that you're not ever looking at just one molecule. And although you generally take just a tiny speck of your molecule in order to take a mass spectrum, even in a tiny speck, you've probably got at least a quintillion molecules, maybe more. So that's why all possibilities will eventually happen. And so before we actually look at spectra, so the first thing that's going to happen when we introduce the sample into the spectrometer is, by any of various methods, we're going to knock an electron out of the molecule. And in this case, we only have these 8 electrons that are in carbon-hydrogen bonds. And so as a result of knocking out any one of those 8 electrons, we're going to have sort of a half bond there between the carbon and one of the hydrogens. And that single electron can then move in either direction. It can move onto the hydrogen and leave the carbon with a plus charge, or it can move onto the carbon and leave the hydrogen with a plus charge. In that case, of course, your fragment is just H+. So I don't think you'll really ever detect H+ at 1 AMU, but you certainly will detect the methyl cation. So, whoops, what have I done? So that will certainly be a thing. And so, well, that's terrible geometry. Sorry about that. Of course, it will be sp2 hybridized, trigonal planar, but I think you get the idea. So where is that going to show up? Well, it's going to show up at a mass to charge ratio. That's the units, by the way. That's the units on the horizontal axis, mass to charge ratio. And since your charge, Z, is going to be +1, it's going to be numerically equal to the mass of the species. And so you just go to your periodic table and look up the most common isotope masses, which again for carbon is 12 and hydrogen is 1. So you have 12 plus 3, we would expect to see a peak at 15. And maybe technically also wanted m over z equals 1 for the H plus, but I think they usually don't even show anything much below 10. I think they just cut off those others because they just, even if you see anything, it's not statistically important. So again, you'll get a sort of a half bond between the carbon and one of the hydrogens. That half bond can then break either way. And so you'll get both cations and both radicals. The radicals are not what you detect, though. You detect the cations because it has to be charged, right? It's mass to charge ratio. If the charge is 0, we're dividing by 0, and that's probably not a good thing. We don't divide by 0 here. At least we try our best not to. What about ethane? Is ChemGraph free to use? No, I'm afraid not. But you know, we might have a site license. So if you go on some of the university computers, you might be able to get it. I don't know. I mean, I feel like we should, or at least on chemistry department computers. But yeah, I don't believe you can just download it for free. So here's our propane. Well, let's look at the possibilities. We can break one of these three, really 6 CH bonds. The ones on the end are all the same. And you'll wind up with a propyl radical and a propyl carbocation. Or we can lose one of these, and you'll wind up with isopropyl radical and cation, only the cations would be visible. That's going to have the same weight, of course, as the propyl one. Or we can break one of the carbon-carbon bonds. So I would put it to you that the pieces we will get are, see if this works, we'll get CH3 plus, we'll get CH3, CH2 plus, we'll get the one propyl cation, and we'll also get the isopropyl cation, like CH3, CH plus CH3. And of course, as you recall, carbocations will rearrange. Whoops, oh, that didn't turn out the way I wanted. Carbocations can rearrange, so likelier than not, pretty much all of the N-propyl cation is going to rearrange to isopropyl anyway, which doesn't matter because they have the same weight. So we would expect to be able to see the methyl cation at 15 AMUs, the ethyl one at 29, because it's 2 carbons, 2 times 12 is 24, and 5 hydrogens, 24 and 5 is 29. So that's how you do it. You just add up the isotopic weights. That's also a sticking point on this. It's no more complicated than that. You just get the most common isotopic weights. And then what about the propyl and isopropyl? Well, they'll both be, m over z is 41, 3, 43, new math. By the way, notice that each time we're adding 14. I guess if you had to memorize one number from this, maybe 14 is not a bad number to memorize. Because if there's long alkyl change in the molecule, I think we'll be looking at octane later on, then you'll tend to see clusters of peaks centered on ones that vary by, or that change by 14 AMUs each time. So methyl is 15, ethyl cation is 29, propyl's 43, butyl's 57, pentyl is 71, and on it goes. So, and you'll see that, I think, when we get to something like octane. What about methanol? Let's go nuts and put in, why did you only find the mass to charge ratio of the first 2? I didn't. The 43, I just ran out of room. The 43 is for both propyl and isopropyl. They both weigh 43. 3 carbons, 3 times 12 is 36. And then 7 hydrogens, 36 and 7 is 43. Is that what you meant? Because I didn't. I found them for all 3. It's just that these 2 were the same. Let me actually make that entirely, completely clear. Just give me one moment. Good. Does that clarify that issue enough? Does that answer your question? That's what I was trying to say. And really, I think realistically, I think you're going to be mainly looking at the isopropyl cation. I think there's going to be very little N-propyl. Not that it matters because they have the same weight. So they'll be in the same peak. So that peak will count for both of them. What about methanol? Let's go nuts and put in a heteroatom. So here's your methanol. And again, all possibilities will happen. So you can expect one of the carbon-hydrogen bonds to break, probably even more so, the oxygen-hydrogen bond will break. Because you can also knock out one of these non-bonding electrons, and that will certainly weaken that bond. So you'll get all possible pieces. You'll get CH3, I'll write them down in a moment, CH3O plus, or you could think of it as CH2OH plus. You'll also get the methyl cation, and I think that's all she wrote. So I would expect that you'll get CH3 plus, which again, we would expect to see at 15. And again, I mean, I think you'll wind up memorizing 15, 29, and so forth, but I don't think there's really any numbers that you need to memorize, except maybe bearing in mind a good trick to remember is the peaks that are separated by 14 AMUs. But you don't need to memorize these. You can figure this out by looking at the periodic table, which I should also mention. Of course, I will include a periodic table with every exam. I would not dream of giving an exam in any chemistry course at any level, freshman, sophomore, junior, senior, without giving a periodic table. I assume those are going to be online and somehow administered on Canvas. I do not yet know how to do that. But by the time we have our first exam, God willing, when the creek don't rise, I will know. And you will not go into the exam without knowing what's going to happen. I just still have to learn how to do that. Oh, the other thing I still don't know is I looked at my email just now, and they still haven't told me when my labs are. So I've yet to figure out when exactly my office hours are going to be. So the CH3 plus is the result if you break the CO bond. Yup. And you will, actually, I think you might also see the hydroxyl cation. You might see that. 1 in 16 is 17. And then, of course, you can break either the oxygen-hydrogen bond or one of the carbon-hydrogen bonds. And how shall we put that? H2COH plus, right? And CH3O plus, right? And again, I'm just running out of room, but this next line refers to those two cations. So they will be 15 plus 16 is 31, right? Yeah, that sounds right. So so that would turn the OH into the radical. Yes, and it can go either way. If you get CH3 plus when you get the OH radical, you get OH plus when you get the methyl radical. And technically, it's always the cations that would you ever see well, you remember, you'll never see any radical alone because you can't detect radicals. Do you mean, would you ever see the H plus at 1? Not in my experience. I don't tend to look at 1 anyway, because knowing that there's H pluses is generally not a very useful bit of information. So, but that's something always to remember, which, no, I mean, I didn't mean to come down on you. It's a perfectly fair and perfectly good question. Please notice how I'm writing down these fragments. I'm always writing down things with a plus charge. So that's something that I would get used to doing when you're identifying peaks. And again, I've put up an old exam with the answer key, plus you'll get to practice an owl. So generally, when one asks about, to identify particular peaks in a mass spectrum, in general, we're looking at cations. So you need to be sure that you're putting down charged species. The only way you can see a peak on a mass spectrum is if the species that corresponds to it is charged. There's no exceptions to that. Must be charged species. What happens when there are double bonds? Well, those can break also, they're actually likelier though to break next door. And I don't know if we're going to have a chance to look at an example of an alkene, but they'll usually break next to the double bond. That's pretty common. And I mean, there are fancy things also. You'll read about other kinds of fancy rearrangements, the McLafferty rearrangement. You know, do you have to know that? More knowledge is always better than less, but those are not the ones that I would go for first. If I'm tasked with finding 3, 4, 5 peaks, I'm going to look for easier ones first, you know, before I go for those. But would they be accepted? Certainly. And again, you'll get some practice on OWL with what you need to put. And I think you'll also get some information on that from the practice exam. I don't promise yours will be just like that, but I think you'll get some information from that. But yeah, double bonds, whether carbon-carbon or carbon-oxygen, can also cause fragmentation. But I'm having trouble thinking of a case where I've seen the double bond itself break. I don't think that's going to happen. I think they're too strong. But you can get pretty stable cations by it breaking next door to the double bond. Good, so I think that's all we need to say about that. Oh, one other thing, this is really important, but it is in your class notes. Please do bear in mind that in order to be able to identify a peak to a structure of a fragment, that needs to be an actual piece of the molecule. So we don't want to go looking for a peak at 29 and then assigning it to CH3CH2+ if there's no ethyl group anywhere in the molecule. Maybe there is a peak at 29, but it would not make sense to identify that peak. It certainly would not make sense to identify it as ethyl cation if there are no ethyl groups in the molecule. So that's very important. Certainly go looking first for things that are actually pieces of that molecule. So good. Let's see then. Octane is a really good one to start with. So we're even here, they were kind enough to give you the molecular weight. The molecular ion will be 114. I think if you add up C8H18, you'll get 114. Not that I don't believe math, but let's just see, 8 times 12 is 96. Indeed, 96 and 18 is 114. And so when you knock out one electron, of course, it's still going to weigh 114. Electrons basically don't weigh anything. Good. So lo and behold, there it is. That peak there is going to be our molecular ion. Usually you can see the molecular ion, not always. You'll sometimes see some spurious peaks above the molecular ion. That's going to be junk of some kind. Because how are you going to get a fragment larger than the original molecule? That's not going to happen. But I can see that there. I would certainly identify that as the molecular ion. It's what you get when you knock out one electron from somewhere in octane. Anywhere, you'll get the molecular ion. By the way, can you see a teeny little bitty peak here at 115? Guess what that comes from? That comes from, I mean, this is next order stuff. You don't go for this at first. But I would bet that most of that is coming from octane with one of the 8 carbons being a carbon-13. And which of them? Well, any of them. And there will be occasional octane molecules with a carbon-13 instead of a carbon-12, to the tune of somewhere like 1% of all of the molecules will have at least one carbon-13 in there. Really, you're only going to see the ones that have one. But of course, there's 8 different carbons in octane. So that's something you'll get to practice on OWL. In general, you can guess how many carbons are in the molecule. If we had, let's say, exact information from exactly how high this teeny peak at 115 is relative to the 114 peak. But I would bet each of you 25 cents American that if we had that number, we would find that the 115 peak is about 8% of the 114 peak. One for each of the 8 carbons in the molecule. So like I said, that's next level stuff. Certainly we try to find the molecular ion first. We might not always find it, but that's what we should do first. And then we see these groups of peaks that look suspiciously evenly spaced. In fact, I'm quite confident we'll find they're spaced 14 AMUs apart. And all of these are going to be successive losses of CH2s. So what would all of the different heptyl cations be? That would be C7H15 plus. So 7 times 12 is 84, last I checked, plus 15 is 99. Lo and behold, I don't see anything there. I guess those peaks are just I guess those fragments are just too rare. So for some reason, we don't see them. They're just not stable enough. Another 14 from 99 is 85. There we go. It turns out to be the center one. I don't know that I'm real confident in terms of guessing what the peaks at 83 and 80, or rather at 84 and 86 are. 86 might have something to do with carbon 13, but you know, we never have to identify all of them. I certainly never try. So I would say 815 comes from, or I'm sorry, I would say that 85 peak comes from all of our different hexyl cations. And if I'm asked to draw one, I would draw any 6 carbon cation. You could even draw CH3, CH2, 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 CH2 plus, and that would be fine. Or you could draw a different hexyl cation, maybe it rearranges, also fine. So 85 minus 14 is 71, there it is. This tallest peak in this cluster is, I would be confident that that's for the various different pentyl cations, C5H11 plus. And you could draw any one of them if you're asked for the structure of one of those cations. I would expect the same to be true in OWL. Minus another 14, 71 minus 14 is 57, 5, 6, 7, there you go. That peak is for our different butyl cations. Here at 41, we've got, 43, I keep doing that. 43 is going to be our propyl and isopropyl cations. And there again, lo and behold, here's 29. That's going to be our ethyl cation. There's only one ethyl cation. There's only one way to put together CH3, CH2 plus. As for 15, can we maybe see a tiny bit of the methyl cation? Maybe, I think I see a tiny peak there. It's possible. But as you see, just from this, even in a simple compound like octane, we've identified with some confidence at least 1, 2, 3, 4, 5 peaks at least, other than the molecular ion. So that's the thing you should be able to do. How would we answer the question, what peaks can we identify? Well, again, the rule of thumb is you need to do everything it says. You don't need to do anything it doesn't say. So if OWL asks you to identify a certain number of peaks, those are the ones I would identify. And I would first go for the low-hanging fruit. But you would make a list of the main ones, just like you said, and certainly always identify them as cations. Right, remember, it has to be a charged species in order to make it on the list, in order to make a peak on the spectrum. It has to be a charged species. So that's what I would suggest anyway. Let's see if we can do any others. Cumene, that might be interesting. Cumene is isopropyl benzene, not that I would expect you to know that, at least not yet. You might learn that later on when we get to aromatic compounds. So what are we going to be able to see? Well, I would expect we'd be able to see the molecular ion, at least I'd hope. Again, they were kind enough to give us that. And there you go, there it is at 120 AMUs. That's going to be our molecular ion. And you may or may not always see, sometimes the molecular ion is so unstable and so readily forms other fragments that you can't even really see it. Here we can see a small peak again at 121. And I would bet you anything, or like I said, at least 25 cents American, that that's going to be for all of the different possible cumenes that have any one of those carbons replaced with a carbon 13. That will have 1 AMU larger. And since since carbon-13 is 1% of all carbon in the universe, since there's, what, 9 carbons, I would bet you anything that peak is 9% as tall as this one. Give or take, it's never exact. Other than that, what else can we identify? Well, let's think of what we might see. We might see this bond break, and so we get CH3 plus and benzene CH2, well, let's say CH plus CH3. That's going to be 15 less than 120 or 105. Bingo, there it is. That's even that we can even call that the base peak, which means the one that's the most intense, the tallest peak. So there you go. I'd be very confident in assigning that peak to be, well, let me actually draw it out for you. It's not like pixels are expensive. I don't need to be so stingy with my pixels. So I would bet this one is at 105 AMUs. What else? That would be true if we broke really any of those. Can we, or rather, I'm sorry, either of these two carbon-carbon bonds to these two methyl groups, they're the same. Could we lose the isopropyl group? I would think we could. If we do, then I would expect, are the biggest peaks the most stable cations? Good question. I think in general, yes, we could expect that. They're the ones that occur the most often, so they should be the most stable ones. Oops. So this one here, I would expect to see that at 43. And what's 120 minus 43? 77. Is it possible we'd see the phenylcation at 77? Phenylcation isn't terribly stable, but I would not be shocked if we could see that too. So let's see. 43, well, there's a little one. So there you go. There is a teeny bit of it there. And I bet we get an almost equally little bit of the phenylcation. What did we say that one was at? 77? You know what? I'm going to add that up just to be sure. It's C6H5 plus. 6 times 12 is 72, plus 5 is 77. Yes. So let's see if we can find a peak at 77. Well, we can. This one here. And that could be for other things also that just happen to weigh 77. But I wouldn't be surprised if that includes some of the phenylcation. It might be that in comparison, these smaller cations are less stable, so we see less of them. Oh, I forgot to look for the methyl cation at 15. Yeah, I can see it there. There's a little teeny bitty peak. That's probably CH3 plus. So those are really the only ones we can. And I'm pretty much running out of time at this point. But notice that one thing that becomes pretty evident is that it's pretty, we certainly get much fewer peaks with a cyclic compound, whether that's a carbocycle or an aromatic ring. I think if you went on onto this website, let's even do it since we have 3 minutes. Let's compare, say, well, you already saw how octane looked. I wonder if they have cyclooctane. What have I done wrong? Let's see if they have cyclooctane. I'd bet you anything we'd get far fewer peaks. Also, I'd have a great deal of trouble identifying any of them. But let's see if they have the mass spectrum of cyclooctane. MS, they do. I lied. It seems to fragment quite a lot. I wonder if we can identify any of these. 112, yep, there's our molecular ion. And again, I bet you each 25 cents American. And I would expect to win about, oh, there's 100 of you. It's 25 bucks, you know. I would expect to win that bet. I bet you anything that the 113 peak is from any one of those 8 carbons being a carbon-13. So let's see here. I did not expect this to fragment so easily, maybe because it's a larger ring. These certainly are looking like they're 14 AMUs apart. So I wonder if, let's see. So again, what was my hexyl group again? C6H11 plus, so it's 72, wait a minute, I didn't do that right. Oh, sorry, C6H13 plus. This is going to have to come with some rearrangement, by the way, because I would have trouble believing that we'd get CH2s at both ends or something like that. Maybe we could. I guess you could have one CH2 at one end being a radical and the other being a cation, and then, of course, rearranging like crazy to form something of the same weight. That I suppose, is somewhat believable. In other words, what I'm talking about here is, I wonder, where's my 8-membered ring? I can draw a stop sign with one mouse click. I wonder if what we're talking about is getting at first a radical like that, and then or rather not like that, but rather changing one of these carbon-carbon bonds into a half bond. I don't really know how to show that, but and then of course this electron will move onto one of the carbons, and you'll get essentially and I really am out of time, but let me see if we can at least identify one of these. 1, 2, 3, 4, 5, 6, 7, 8. I'm saying that at one end you'll get CH2 plus, which will quickly rearrange into something of the same weight but more stable, since that's a primary cation. And over here we get a radical. Well, that's still a charged species, so I would expect to be able to see that. So what's this guy at? It's like C8H16 plus. Did I do that right? Let's figure out where that would show up. 8 times 12 is 96. 96 and 16, last I checked, was 112. Can anyone confirm or deny that? 96. Yeah, 112. Good, thank you. No, I do make math mistakes. So let's see if we can, wait a minute. Oh, what am I doing? Of course, that's the same as the molecular ion. So if we lose CH2 from that, 112 minus 14, and maybe we won't see this one, is 98. Oh, well, that's awfully close. I see one at 97. I wonder if it somehow loses another hydrogen and makes a double bond. Possible. And then, of course, once you get that one, that thing's unstable and starts losing one carbon at a time, CH2s each time, getting these other fragments. Anyway, I'm sorry, I'm out of time, but I wish I had time for more examples, but that should at least get you started in terms of what you need to be looking at when you look at mass spectra. Certainly take a look at the old exam, take a look at the OWL assignments, but important question. I was at 20. I had a professor, I stole that from another professor. I would say if it does refer something, then if you should be ashamed, I should be equally ashamed, because I don't know of what it would refer to. So that must have been, let me think now. That must have been when I was in grad school. I must have known someone who said that, because I went to the University of Michigan. Michigan's very close to Canada. That's the only place you would really refer to American as opposed to Canadian. So, yeah, I don't really know. I am sure that every one of you is much more cultured than I am. Anyway, we're out of time, so I will see you all on Wednesday.